Yeah, if there's a driving force, you should balance it. So I'll go ahead and read off what you have.
LiSO2.
LiSO2.
Is that lower or two? Oh, no. It's like it's LiSO3. Three.
SO3 is correct. Is the rest of it right? LiSO3? Li2SO3? Li2SO3 is right. Li2SO3 plus
Na3PO4.
Na3PO4. And this produces
Li3PO42. 2.
2, like this.
Yes.
Okay, what is the phosphate though?
Wait, just kidding. No, it's not. No, it's not. No, it's not.
Okay.
It's not. Not 2.
Okay, what is it then? Li3
Li3PO4.
PO4. Phosphate's a 3 minus, so we'll need 3 lithiums to balance it. So that's where that formula comes from here. You don't write charges. You know, what's the charge on sulfite? We never write charges here. The beginners write charges there all the time and don't erase them. Problem is if somebody saws that, they're going to think, what are you doing? This is ridiculous to put the charge there because this is not an ion. This is a compound. But of course, you want the charges there so it'll help you figure out the correct ratio of ion. But you could do this as a side, but don't write it, as the actual formula. Li3PO4 and
then
Na2SO3. And what did you get as your driving force?
PPT.
What is the PBT? Which one? Both of them?
Phosphate.
The phosphate's a PBT?
Yeah.
So you're going to solve it here. And what's the rules for solubility for that PPT?
Phosphate is insoluble.
Except for
Ammonium and group.
and lithium is a
Oh.
yeah. This is both of these are aqueous. So both of these are group 1 salts. And so neither will precipitate. Then what do we look for? Gas? Do either of those? No. Yeah, stronger to weaker acid. Do we see a stronger to weaker acid there? And so what we have is we have no driving force. Therefore, we say NR. Yeah, NR just stands for no reaction. That's right. But when we do this, we need to do this in this context, no metathesis reaction. Because that's all we're looking at, are metathesis reactions, right? Yeah. But there are other potential reactions that could occur. You must consider what? You must consider, well, how many different types of reactions are there
For metathesis?
in the world? Yeah. No, how many different types of reactions are there in the world? Would you say billions of reactions going on every day? Chemical, biological reactions, billions. Well, what would you say is a reasonable number? How many different types of reactions are there? Innumerable?
Yeah.
Pretty much innumerable. And so the only way to learn them is to memorize all the reactions that occur in nature. Is that it? No. No, we don't want to do that. But if you look at the list in your book, the list in your book is not comprehensive. We need something more comprehensive. And so this is why, it's okay. You can memorize those reactions in the book and in the supplement, but it's not comprehensive. So we need a comprehensive. Well, this is comprehensive in a broad scheme. How many different types of reactions are there? Metathesis, acid base, and redox. And so if we classify those are the three basic types of reactions based on driving force. Let's consider acid base. And redox. Potential reactions. It could be an acid base or potentially a redox reaction that occurs here. When we consider these reactions, we look at the major species in solutions. What we're going to do is we're going to look at the major species present. And so this is some of chapter 9. Which deals with solubility and electrolyte properties. Okay, what we do is we look at the reaction mixture as given. So in considering other potential reactions.
Are we done with chapter 8?
No, not done with chapter 8. But it's going to be eight, 9, and the supplement all together, basically, because I classify the reactions differently than in the book. We can memorize the reaction types that are given in the book, but since it's not comprehensive, I'm not even going to bother. I'm just going to look at the three general types of reactions. It being the three general types of reactions, we learn metathesis reactions first, and then we move on. But before we even leave this, we need to look at reactivity of major species present. And so the major species that are present here are these. So in this example, we have lithium ions, we have sulfide ions, we have sodium ions, we have phosphate ions, and we have one more major species, and that is water. Water is called the solvent. This is what all these things are dissolved in, the solvent for this. And then what we do is we look at the acid-base properties and the redox properties of these, and then consider acid-base and redox properties. So how do we consider the acid base and the redox properties? Okay, so let's take a look here at part 2. There are three types of acid-base reactions based on how you look at it structurally. These are three definitions of acids and bases. Historically, it started off with Arrhenius. Arrhenius' definition was way too narrow. Arrhenius just defined an acid as H plus and a base as OH minus. But not all acids have H plus and OH minus. Not all bases do. And so we have a more broad definition, which is Bronsted-Lowry, but Bronsted-Lowry is still a little bit too narrow of a definition. And finally, Lewis came along. Lewis is the most comprehensive definition of what an acid and what a base is. In the Lewis definition, I'll just tell you, an acid is an electron pair acceptor. So if you have a pair of electrons, it accepts it. A base is an electron pair donor. We haven't gotten into the structure of these yet. And so we aren't really going to talk too much about Lewis yet, just now. But Lewis is definitely the most comprehensive definition of an acid and base, but it's also the most difficult one as well. And so what we're going to do is we're not going to get rid of Bronsted-Lowry. We could get rid of 1 and 2 and just use 3, but 2 is easy. You know, acids have H+, bases, exception, H+. Not all bases have OH-, so Bronsted-Lowry, it just has to accept H+, like ammonia. Ammonia is considered a base, it just has to accept H+. And so in a Bronsted-Lowry acid-base, this is going to be the easiest. These are the easiest to predict. But what we do is we transfer an H+ from the acid to the base. That's it. And so acids are H+ donors, bases are H+ expectors. We need to determine the driving force. The driving force is just simply stronger acid to weaker acid, which we've seen before. Likewise, stronger base to weaker base. And so the general method for acid-base reactions is we inventory it. This is inventory here. Inventory is just pick out the major species in solution. Here, that's it called an inventory. And then we determine the strongest acid and the strongest base present. Well, in order to determine the strongest acid and the strongest base present, we go to the acid-base chart. I don't know if I put it in here. Did I put it in here? I need to just check really quick. No. I have to go back to PowerPoint 1. Or it's on Piazza. We go to the acid-base chart. And then we just look. Okay, do you see lithium ions on the acid-base chart?
No.
No. And so what we say is either, do you think this acid-base chart is abridged or do you think it's comprehensive? Yeah, of course there's a bridge. There's too many acids, too many bases. But acids either have an H at the beginning or an H after the COOH. Recall that? And lithium, do you see any hydrogen atoms lithium can donate to be an acid? Is there any H? No, there's no H, so we call it neutral, N, for neutral. Or not, it's not. How about sulfite? Do you see sulfite on the acid side? No, obviously sulfite's not going to be on the acid side because it's missing H. There's no H. It's not an acid. Do you see sodium ions on the acid side? No. So sulfite I'm not going to say anything, but sodium I'm going to write neutral. Do we see phosphate on the acid side?
No.
No. But I'm not going to write neutral because phosphate and sulfite occur on the opposite side, which I'll talk about.
Phosphoric acid.
Phosphate and phosphoric acid are two different things. Did we have any phosphoric acid? No, we had sodium phosphate. And so if you're putting phosphoric acid in there, it's magically appearing because we weren't given any. Now, if they said phosphoric acid, for sure. But phosphate is different than phosphoric acid because there's no hydrogens on there. This is not an acid. Okay. How about water? Do you see water? Even though water is not one of the reactants that was given, it's present because these are aqueous. And so there's always water present. Do you see water present on the acid side?
Yes.
Yeah, there it is. So water is an acid. And so we label this A for acid here. All right, now, this chart is interesting because this chart has what's called the base, the conjugate base. So when the acid loses an H+, it forms the conjugate base. So, for example, perchloric acid loses an H+, it forms the perchlorate ion. Perchlorate ion is the conjugate base because if it gains an H+, it reverts back to perchloric acid. And so all these bases are capable of regaining the H+. If nitrate gains the H+, it becomes nitric acid. So these are the conjugate bases here. And the conjugate bases, it makes sense because if the acid is strong, you know what a strong acid means? A strong acid means it easily loses the H+. So it freely loses it. If it freely loses at H plus, then that H plus can attack whatever base it wants to attack. And if this one easily loses the H plus, that means perchlorate doesn't really hold on to the H plus very strongly. If it doesn't hold on to the H plus very strongly, we call it a weak base. In fact, these are so weak, we don't even really consider it. Like chloride, you know, chloride's not really considered a weak base. It's considered pretty much neutral. And that is, bases have the opposite action of acid. So if you have too much stomach acid, you know, you have too much stomach acid and you ran out of milk of magnesia, you ran out of whatever else they have. What else do they have? So you ran out, but can you use sodium chloride to neutralize your stomach acid? Could you use salt? And so this is what it means to be extremely weak. This one, the chloride's not going to pick up the H plus in your stomach acid. The strongest ones are going to be down here at the bottom. And so it's the opposite. Like methane. Methane does not want to lose its hydrogen. Methane we don't even consider an acid, but if something were to pluck off that hydrogen as a proton, we'd be left with methide ion. Methide ion would be the most powerful base on this chart. On that chart over there in the back of our classroom, amide, NH2 minus is the most powerful base on that chart, amide. Ammonia is not even thought of as an acid normally. Ammonia is thought of as a base, but it could react. So let's go to lithium ion. Do you see lithium ion? No, lithium ion doesn't occur anywhere on the chart, nor does sodium ion, so that's why I wrote neutral here. But sulfite does. Do you see sulfite on this chart? No, I see sulfate, I don't see sulfite. However, on this chart back here, you can find sulfite. You look on the right side, this chart back here, about midway up on the right side, do you see it? A little more than midway up on the right side, far right, do you see sulfite? What that means is it's a moderate base. It's what we call a decent base, sulfite. And so what we'll do is we'll write base here for B, for base. How about phosphate? Well, phosphate occurs on this chart because phosphate's pretty common. So it should be here. Do you see it? You know what? I screwed up. On my PowerPoint, I screwed up. Let's see if I screwed it up on Piazza. No, Piazza is okay. What happened was the person who made the chart in the PowerPoint slide accidentally forgot this one. Accidentally forgot to put phosphate in there. But phosphate's on there. Where does phosphate sit? Phosphate's borderline what we call strong base. I'm not going to make you memorize the strong bases, but these are the strong bases here. And phosphate is almost a strong base. But since it's on this side, we call it a weak base. And so phosphate is a base here. And so what we do is we use the chart to figure out what our acids are and our bases are. Okay, then we determine the strongest acid and the strongest base present. So there's only one acid present. What is it? It's water. And so this is going to be the strongest. Now, which is a stronger base, phosphate or sulfite? Sulfite is a mid-range, phosphate's borderline strong. So phosphate is a stronger base. No. Okay, so we pick the strongest acid and the strongest base present. Then we transfer a single H plus from the acid to the base. And so what we'll do is we'll transfer a single H plus. And so what's going to happen is the acid is going to lose an H plus, and the base is going to gain it. So what we'll do here is we'll just take phosphate, PO4 3 minus, which is the strongest base, plus the strongest acid. And all an acid does in Bronsted sense is donate a proton, donate a hydrogen on the base. And so what we're going to end up with is H plus and phosphate. Well, that's a acid anion. HPO4, what's the charge on HPO4? HPO4? It's going to be 2 minus. 1 plus, 3 minus gives us a total net charge of 2 minus. And hydroxide. Water is going to lose an H plus. Okay, then we determine if there's a driving force present. So let's take a look for the driving force. The driving force is, we often think of a competition, forward versus reverse. Now, which way is it going to go? Which way is the downhill direction for this? And so what we're going to do is we're going to reverse this. In the reverse direction, who acts as the acid, who acts as the base? Okay, is this the acid or is this the base going backwards? This is the acid because it's losing an H. And this is the base. And then we compare these two. We want to go from stronger to weaker. And so let's compare water versus, what did I call it, monohydrogen phosphate. This chart is not good. Why did I go back to this one? I need to go to this one. Water versus monohydrogen phosphate. Which one's a stronger acid? Water or monohydrogen phosphate? Monohydrogen phosphate. Acid strength increases. Those go this way. So it turns out that this is a stronger acid, this is a weaker acid. So which way is the downhill direction? To the left. Does everybody see that? That means that the bases got to follow. If the acids follow this, the bases must follow this. So that means hydroxide must be stronger than phosphate. And is that the case? Hydroxide is stronger than phosphate. That's correct because it increases this way. So this is stronger. This is weaker. And so what we say is here, the driving force is to backwards here. The downhill direction is this way. And so what we'll put is NR here in quotation marks. The reason I'm going to put NR in quotation marks is it's because of this. You know, how big of a difference is there in the strength? They're right next to each other. And so that means there's not that big of a difference in strength. And so if I'm thinking about it, yes, this is the downhill direction backwards, but is it a steep hill like this? Or is it a very shallow grade like this? A very mellow? It's very mellow like this. When it's very mellow like this, then something funny happens in chemistry, and we end up with what's called a dynamic equilibrium. That is, yes, this side is more favored, but how much more? Just a little bit more. If it's a little bit more favored, then what we end up with is a mixture at the end of this. You know, a little bit more of this, but it doesn't mean there's none of this because it doesn't require that much energy to climb this little hill up to here. Does that make sense? And so sometimes we show this dynamic equilibrium like this. Sometimes what we'll do is we'll show a big arrow or a bigger arrow going backwards and a smaller arrow going forward to say that, yeah, you can expect maybe a little bit of this to form, but this is favored thermodynamically. Versus if there's a huge difference in the strength, let's say we're comparing water with perchloric acid, If we compare water with perchloric acid, which one's stronger? Perchloric, it's off the chart here. And so if we're going from perchloric acid to water, then that's hugely favorable, like this. And we expect it to be all product in that case, you know, if water is the product. Does that make sense? And so it depends on how big the difference is in the strength. That tells us an indication of the driving force for this. And so we see this happen. Remember how ammonia participates in metathesis reactions? You know, how does ammonia participate in metathesis reactions? Because ammonia is a molecular compound. Metathesis deals with ions. How does ammonia participate in metathesis? Did you have a chance to review Thursday last week? Yeah, okay. What did you get? How does ammonia participate in metathesis? I'll put you on the spot. A little bit of a hint. Ammonia reacts with?
Or like any liquid.
Well, in this case, water. I don't know how many people wrote down this reaction. This is what I wrote on the board. Ammonia plus water. I myself write everything down that I can. Otherwise, it's just lost information. Ammonia plus water yields what? Yeah, yields NH4 plus hydroxide. Now in class, I might have done two things. I might have done this. I don't know, did I do that in class?
Yes.
I did that in class. Do you know what this means?
It's more going this way.
This means the downhill direction is
To the left.
backwards, to the left. This is more stable. Well, what we're doing is we're comparing this. Can you tell me what the acid is and what the base is here?
Acid is water.
Acid is water, base is
Ammonium.
ammonium. And then if we go backwards, which one's the acid, which one's the base?
NH4 is the acid.
Yeah, this one is the, and then we compare it. It turns out that this is stronger, this is weaker, this is weaker, this is stronger. And so we'll compare ammonia and hydroxide here. When we compare ammonia and hydroxide, well, it looks like ammonia is significantly weaker, right, than hydroxide, but not hugely. You know, it would be huge if it was way up there. And the same thing here, when we compare ammonium and water, yes, ammonium is a stronger acid than water, but it's not like perchloric acid, right? And so in this case, it's a little bit more steeply like this, so we should form a little less of this, you know? Over here, it's not so steep, and so we should form more of this, you know? And so what we have here is, we have something called a dynamic equilibrium. When we have ammonia and water, an acid-base reaction occurs. This is a Bronsted acid-base reaction. In this Bronsted acid-base reaction, we form some ions, and those ions can then react in metathesis. And so we get a combination of reactions here. And so in this case, very little. You know, if I were to do this as percentages, less than 0.1% reaction occurs. It's like 99.9% this and 0.1% this. And so, you know, it's kind of still steep. Over here, it's a lot more. You know. But still, both of these are unfavorable. So either we could call these both no reaction because there's no driving force. There should be no driving force because we're going from weaker to stronger. We need to go from stronger to weaker. But then we got to look at it in a little bit more detail, like how big of a difference is there? You know, how steep is that decline? If we really want to understand, you know, the chemistry that's happening here. And so this is the acid base. These are things we got to consider because not all reactions are metathesis reactions. We got acid base and we got redox. And so here, while we we took care of acid-base. Do you see any acid-base reactions? No. Okay, the next thing we look at is for redox. How should we look for redox? Well, how are these steps? Well, the inventory might be a little hard to do because you haven't had much practice with that. But how are these steps? Was that hard? Was it hard to find the acid and the base on the chart?
No. So the chart will be given?
The chart will be given.
Oh.
The chart, you don't have to memorize the chart. The chart is given. All you have to do is find the species on the chart. Was that hard?
No.
Or was that pretty easy?
Pretty easy.
It's pretty easy, but some people will come up with a mental block every semester and say it's too hard. It's too hard because it's not in the book. And that's what makes it too hard. If it's not in the book, was that too hard? I mean, could you figure it out without the books? Yeah, you should be able to. It's not that hard, actually. Okay, now the next one. Well, let's see. Let's try to get some more practice. Some reactions overlap, the categories. So for example, we did this one already, phosphoric acid and sodium hydroxide. Do you remember doing that? What did it form? It formed sodium phosphate and water. Well, if we do this one using the Bronsted approach, we do it a little bit differently. And so this one, phosphoric acid is H3PO4, sodium hydroxide is NaOH, and then we see what forms there. Now the Bronsted approach is we inventory first, the major species. And so what is the inventory here? Then we got to ask ourselves this. We got to ask ourselves, is water capable of pulling it apart, So for example, if I have H3PO4 in there, does water break apart? H3PO4, is that molecular or lattice? What type? Acids are going to be molecular. If this were metal, like sodium, it would be lattice, right? Or magnesium, it would be a lattice. But this is just H, so this is molecular. Acids are all molecular. In general, acids are molecular. So are the water molecules capable of pulling apart the molecule?
Yes.
Some yes, some no. In this case, it's not capable, and so the inventory is H3PO4. It's because it's a weak acid. Weak acids, what's the difference between a weak acid and a strong acid? A strong acid, does it easily lose the H plus, or is it? Strong acids easily lose the H plus. Weak acids, it's harder. They hold on to the H plus more tightly. So if water comes along and tries to pluck an H plus off a weak acid, it's not successful. The only thing that water can pluck an H plus off is a strong acid, because strong acids lose the H plus easily. So this is a weak acid. There's water around. Water can't break it apart. However, sodium hydroxide, that's a lattice, ionic lattice. Can water break apart the lattice? Is sodium hydroxide soluble in water?
Yes.
Yes. And then when sodium hydroxide dissolves in water, what happens to the lattice? It's completely broken apart. And so what we see for this is we see that the water molecules are going to pull on the ions and then separate it into dissolved species like this. And so this is what we call the inventory here. We break apart the sodium hydroxide because it's soluble. It's a soluble lattice or soluble salt. And then we have water here present as well. And so what we're going to do is we're going to look for acid-base reactions here. Now, phosphoric acid, is that an acid or is that a base or what is that? It's an acid, obviously, from the name, it's an acid. Some acids can act as bases as well, like water. Water can go either way. It can be an acid or a base. I forgot to write that earlier. Shoot. I forgot to write it earlier, but it's all right. I erased it already. Sodium ions are neutral. Hydroxide, base. Hydroxide's funny because hydroxide, let's take a look at our chart. And so, our chart is a bit funny. You got to be careful with our chart because our chart is going to show all possibilities. And if the first time you're going to look at this chart is going to be right before the test, you're going to be in trouble, most likely, because certain things are confusing regarding this chart. One is this. Hydroxide is a strong base. Oh, a strong base. This is borderline for strong bases here. So hydroxide is a strong base. What's it doing over here? It's also a terribly weak acid. But it could go either way, so we're going to write it. And so I'm not going to write strong, powerful base here and terribly weak acid. I'm just going to write base acid. It can go either way. Base is, of course, preferred. Water?
Acid.
Water is a weak acid. But if I look on the base side, I'll see it occurs on both sides. If it occurs on both sides of the chart, then we call it amphoteric. If it occurs, any species that occurs on both sides of the chart is amphoteric. Phosphoric acid only occurs on one side of the chart, and so that's an acid. And so these two species are amphoteric species. Amphoteric is the word we use for that. But it doesn't matter because all we do is this. We look for the strongest acid. How many acids do we have present? Well, 3. 1, 2, 3 acids present. Out of these 3, which one's the strongest? Phosphoric. And then out of the 2 bases that are present, which base is strongest? Hydroxide. It's the strong. And so the acid is going to be phosphoric acid, the base is going to be hydroxide. And so the reaction is going to look like this if we did this Bronsted-Lowry. If we did this Bronsted-Lowry, we're going to take H3PO4 plus hydroxide. And it's going to form what? Water and it's going to form H2PO4 charge. Minus. 2PO4 minus plus
Water.
water. All right, again, we got to look. Which way is the downhill direction? Is it going forward downhill or is it going backwards downhill? So what we're going to do is we're going to look at it from both perspectives. So we're going to stand over here and then look, is this downhill this way? So which one's the acid? This is the acid, this is the base. Then if we go backwards, we look from this perspective and see which one of these is the acid, which one is the base. Both of these are amphoteric. Did you know dihydrogen phosphate's amphoteric? And water is amphoteric. But even though it can go either way, in this combination, it can only go one way. And so here, yes, this dihydrogen phosphate's amphoteric because it occurs on both sides of the chart. Dihydrogen phosphate is a decent acid. Do you see that? It's also a pretty poor base. And so it's a very weak base, pretty strong acid. Is it going to act as the acid? Maybe, maybe not. We don't know how it's going to act because it depends on who it reacts with. That's going to tell us how it reacts. And so looking at going backwards here, who loses the proton? Who gains the proton? Yes, I just told you that dihydrogen phosphate is a better acid than it is a base. But in the context of this reaction, is it an acid? No, it's the base. And so, yeah, okay, dihydrogen phosphate's the base going backwards because that gains an H. And who loses the H? The water. Now, water is equal. It doesn't care. Water is equal in its ability as an acid, as a base. And therefore, water is what we call like pH neutral. It can go either way easily. Whereas this would not be pH neutral. If I had dihydrogen phosphate, it's a much better acid than a base, so it's going to be like an acid more than a base. But going back to this, here, we want to see which one's stronger, phosphoric acid or water? Hydroxide or dihydrogen phosphate? And so we have driving force here. This is driving force. Now, I wrote on the side we compared to metathesis. I wrote on this slide we compared to metathesis. In metathesis, we do full-on reaction. You know, this is step one of the reaction. If we have more hydroxides, then this can act as an acid. If there are more hydroxides present, they'd attack this. And so, do you have the reaction with phosphoric acid and sodium hydroxide or potassium hydroxide from yesterday? Take a look at how we did that and compare. Tell me how it compares to this one.
Is it always going to be acid base acid, or like could it be acid base?
No, it's always going to be like that. It's always going to be like this. It could be base. We could do base acid, but it's going to be
Base.
It depends on how you write it. But if people it depends if they wrote the water first, then it would be screwed up. But if I kept them in the same position, then it's always going to be flipped. That's what we call conjugate relationship. It's flipped. The acid forms the base forms the acid. It's conjugate. So these are, again, the question was about this, noticing there is a pattern here, and that was a very, very keen observation. The pattern is these are conjugate pairs. And so the acid forms the base forms the acid. These are what we call conjugate pairs. And there's a seesaw relationship with conjugate pairs. If the acid's very strong, its conjugate base will be very weak. If the base is very strong, its conjugate acid will be very weak. It's a conjugate relationship because it's, the ability to hold on to the H+. So do you see it? Do you have it in your notes? The difference is in metathesis we do full-on reaction. We react everything all the way. And so what we did was we reacted all three hydrogens on here. For Bronsted, we just do one at a time. So here, this is one at a time, and we'll just stop after one. You could do more. If they said excess, then we would have done more. And so for Bronsted, we're only going to transfer one. Even though there are three hydrogens on phosphoric acid, we're only going to transfer one. solutions of sodium monohydrogen phosphate and potassium hydrogen sulfate are mixed. So let's take a look at this one next. Sodium monohydrogen phosphate, what's the formula for that? Well, this one maybe I'll do up here. Sodium ion, what's the formula? Monohydrogen phosphate, one hydrogen and a phosphate. What's the charge on that? This is going to be 2 negative, good. And so what's the formula for this? Na2HPO4, correct, good. Plus potassium hydrogen sulfate, HSO4 minus. So we're going to have KHSO4. So that works out okay. And then what we're going to do, hey, wait a minute. This looks like, to me, I recognize this as not as a bronze acid base. I recognize this as a metathesis. And so one, I'm going to try metathesis. Because automatically this jumps out. This is metathesis. This is AB plus CD. You know, this is my A, this is my B, this is my C, that's my D. This is an AB plus CD reaction, which we call double replacement. And so what are the products here? NaHSO4, good, and KHPO4, K2, yeah. We've got to balance it, but this is my AB plus CD yields AD plus CB. Then we look for driving force. Is there driving force for this? Sodium and potassium salts are all soluble, so no precipitate. How about, do these form a gas?
No.
No, these are salts. They're stable salts. Are we going from stronger acid to weaker acid? No, there's no change, you know. We have HPO4 2 minus over here on the left, we have HPO4 2 minus on the right. Even though that's an acid or base, it doesn't change. Right? And so there's no driving force. Therefore, no reaction. But should we say no reaction? No metathesis reaction, right. And so we need to be specific. There's no metathesis reaction. All right, if there's no metathesis reaction, then we should look at next, we should look at Bronsted acid-base reactions. And so we're going to go to Bronsted. For Bronsted, we got to look at the inventory. The inventory are the major species in solution. The major species are going to be impacted depending on what water does. And so, is water capable of breaking, what type of structure is that? Molecules or lattice?
Lattice.
This is lattice, salt. This is a salt, metal plus non-metal, salt. Molecule would be like H, you know, H. So this is a soluble salt. When a salt dissolves in water, what does water do? Breaks apart the crystal ion by ion. And so what's going to happen here is we're going to get sodium ions. Now we got to think about this ion. Does this ion stay together, or is water going to pluck the hydrogen off that? No, water is only capable of plucking the hydrogen off strong acids, because strong acids easily lose the hydrogen. Weak acids hold on to the hydrogen. And so water is not capable of it, and so this whole thing stays together as HPO4 2 minus. Over here, this is another salt, soluble salt. And salts, when they dissolve in water, the lattice gets broken apart into what? K plus and HSO4 minus. Now, can water pluck the hydrogen off here? No. Because HSO4 minus is not a strong acid. H2SO4 is, but HSO4 minus is a weak acid, and that's going to hold on to it. And then there's one more species. What's the last species?
The water.
The water. All right, now I have to consult the chart. So, do sodium ions occur on the chart?
No.
No. Sodium ions are not good proton. They don't have any hydrogens to donate, and they don't want a hydrogen ion. They're both positively charged. HPO4 2 minus. Does that occur on the chart? Let's take a look. Here it is. Do you see it? Actually, it occurs here, right? And it occurs here. And so it makes, what do we call it when it's on both sides of the chart? Amphoteric. So HPO4 2 minus is amphoteric. It's both an acid and a base. So we'll just write A/B because we don't know. Do we know which way it's going to react? No, not yet. Not until we combine it with something. Potassium ions, neutral. HSO4. It's an acid, yes. Sure, it's an acid. HSO4 minus is a pretty decent acid. It's up here. It's pretty decent acid, but it's still a weak acid. It's below this line. This is the dividing line. The strong acid's up there. These are the weak. But it's stronger than phosphoric. HSO4 minus is a stronger acid than phosphoric. But do you see HSO4 minus on the other side?
Yeah.
Yeah, here it is on the acid side, but on the base side it's up here. The bases up here are good bases or the worst bases? Some of the worst bases. These are some of the worst bases. Think of chloride. Is chloride good at neutralizing stomach acid? Like table salt. You run out of antacid, you're going to use table salt instead. It's not going to work because chloride is not good at neutralizing acid. But even I don't care, it's bad, but we're still going to put it there as an acid base because it's on our chart. Water is an acid base. So we have 3 acids. Out of these 3 acids, which is strongest? HSO4 minus. And then we have 3 bases. Out of these 3 bases, which one's strongest? Let's see. Well, water is not a very good base. Water's here. You see that? And then let's go down the list. That's water, and then we have HSO4 minus. HSO4 minus happens to be worse than water. You see, HSO4 minus is the worst base we have here. It's the worst base, and then it would be water, and then HPO4 2 minus. Where's that? Here it is. HPO4 2 minus is decent. It's a decent base. And so this will be our base. And so what we're going to do is we're going to take our acid, HSO4 minus, and react it with our base, HPO4 2 minus. And so the acid loses an H plus. And so what are we left with? If this loses an H plus, we're left with SO4 charge, 2 minus. Good. And if this gains an H plus, what does it form? H2PO4 minus. And then we have 3 amphoteric species, and all these depend on how we label this. And so this is the acid, this is the base going forward. Now, if we want to go backwards, is it uphill or downhill? So we got to look, going backwards, which one's the acid, which one's the base? Well, this can't be the acid, there's no H. So that can't be the acid, this has got to be the base, this has got to be the acid. The acid loses the hydrogen. And then let's compare, which one's a better acid? Dihydrogen or hydrogen sulfate? Okay, here's dihydrogen here. Well, actually, where is dihydrogen?
Right there, there.
Oh, here it is. This is dihydrogen, and that's hydrogen sulfate. Yeah, hydrogen sulfate's considerably stronger. Not huge, but still.
Without looking at that chart, do you know that hydrogen sulfate is stronger because it has one less H?
Without looking at the chart, it's not based on the number. Sometimes the numbers will tell us, like for example, HPO4 is, as far as acids go, HPO4 is the worst acid, H2 is better, H3 is the best, more hydrogen. But comparing, let's say, this and this, it requires more in-depth structural analysis, which we haven't gotten to yet.
Okay.
And so we just use
Look at
the
the
chart.
chart.
Yeah. All we're trying to do is get familiar with the chart. If we get familiar with the chart, we see how things behave. That's all we're trying to do. We're not trying to memorize the chart. And so what we see is there's a driving force. If the acids follow this, then the bases must follow. And so the bases must follow unless we made a mistake. And so that means monohydrogen phosphate must be a better base than sulfate. Let's take a look. Monohydrogen phosphate must be a better base than sulfate. It is. It is. And so we have driving force. And so we got no reaction for metathesis, but we did get a reaction for acid base. And so if we would take this and mix it together, we'd end up with sulfate and dihydrogen phosphate. How about redox? How about redox? Okay, this is the chart for acid bases, and we only transfer one H. But what redox is, and acid-base reactions are called proton transfer. Redox reactions are called electron transfer. And that's this chart here. It's a bit more complicated because it's not just a single proton that's being transferred. We have 2 electrons, 6 electrons, 5 electrons, different numbers of electrons transferred, 10 electrons. Protons are transferred. And in redox, it's not protons being transferred, it's electrons being transferred in redox. But the procedure is exactly the same. The procedure is we inventory it, and then we identify the species. And then take the strongest and react those two. So we'll do redox a little bit later since it's a little bit more complex. We'll take a break now. And then,